We're looking at the Brønsted-Lowry definition of acids and bases. An acid is a proton donor, and a base is a proton acceptor. To find the conjugate, we either add or remove an H price. If you have an acid, remove a proton to get its conjugate base. If you have a base, add a proton to get its conjugate acid. Let's work through each one. HBr is clearly an acid. Remove H price and you get OH as a base. Add H price and you get H2O. For the acetate ion, it's a base. Add H- to get acetic acid. HOCl is an acid. Remove H- to get OCl monos. Finally, HO- is amphoteric, but it acts as an acid here to get azocoordinamers. All right, everyone. Here are our 3 main learning goals for this unit on water ionization and pH. First, we need to understand what Kw actually is. It's a special equilibrium constant that describes how water molecules ionize into hydronium and hydroxide ions. Second, we'll explore the direct mathematical relationship between pH and hydronium ion concentration. They're inversely related using logarithms. Finally, we'll master the calculations, converting between pH, pOH, and ion concentrations using the formulas and the Kw value. These 3 objectives build on each other, so by the end, you'll have a complete toolkit for working with acids, bases, and neutral solutions. Now let's look at what success looks like for you in this unit. By the end, you need to master 2 concrete skills. First, you'll be able to write out the balanced equation showing how water molecules split apart into hydronium and hydroxide ions. This is the foundation for everything else. Second, and this is crucial for problem solving, you need to be able to work fluently between all 4 key values: pH, pOH, and the actual ion concentrations. If I give you any one of these values, you should be able to calculate the remaining 3 using the relationships we've discussed. These criteria define mastery for this unit. This slide introduces section 15.1, which focuses on aqueous solutions and pH. We're now shifting into the practical application phase of everything we've just covered. This section will deepen your understanding of how pH works in real solutions and give you the tools to predict and calculate pH values in different scenarios. Think of this as bringing together the water ionization equation and those 4 values we just discussed into a cohesive framework. We'll explore what happens when acids and bases dissolve in water, how to use the relationships between pH, pOH, and ion concentrations to solve real problems, and develop intuition about the pH scale itself. Here's what's actually happening in pure water. 2 water molecules collide, and one acts as an acid, donating a proton to the other water molecule, which acts as a base. This creates a hydronium ion and a hydroxide ion. This is autoionization, or self-ionization. Notice the double arrow. This is reversible and reaches equilibrium. In pure water at 25 degrees Celsius, only about 2 in a billion water molecules are ionized at any given moment, but the ions that do form are crucial to understanding pH. This equilibrium is the foundation for everything we calculate moving forward. Now we're introducing 3 critical new concepts. First, water is amphoteric. It can donate or accept protons, which is why it can ionize itself. Second, we need to understand Kw, the water dissociation constant. It's the equilibrium expression for water's self-ionization. When you multiply the concentrations of hydronium and hydroxide ions in pure water at 25 degrees Celsius, you always get 1.1010 small. This is a fundamental constant at this temperature. This relationship will become your key tool for solving pH and pOH problems and understanding whether solutions are acidic, basic, or neutral. Now we're applying Kw to classify solutions. Here's the key insight. In pure water, both ion concentrations equal 1.10 mmol, so they're perfectly balanced. That's neutral. But when you add an acid or base, you shift this equilibrium. If hydronium ions increase, hydroxide ions must decrease to maintain W equals 1.10, making the solution acidic. Conversely, adding a base increases hydroxide and decreases hydronium, making it basic. You can always use Kw to find one ion concentration if you know the other. Now let's practice using Kw to calculate the missing ion concentration. In the worked example, we're given the hydronium concentration and need to find hydroxide. Watch the algebra. we rearrange the Kw equation by dividing both sides by H3O- to isolate OH-. Then substitute the values and divide carefully. Remember your scientific notation rules. Notice the exponents. -14 minus -5 gives us -10. Now it's your turn with that 0.0045 m solution. Set up the same rearrangement, plug in the numbers, and solve. This is the practical skill you'll use repeatedly in acid-base chemistry. Great. Now let's work through your practice problem together. You have 0.0045 m of hydronium ions, which is already in decimal form, not scientific notation yet. You'll substitute this directly into the rearranged equation. Kw divided by H2O gives you OH-. When you divide 1.0 x 10 -045, you get 2.2 by 10 -2. Notice that hydroxide concentration is extremely tiny. That makes sense because this is an acidic solution with lots of hydronium. The key skill here is confidently handling both decimal and scientific notation forms without converting unnecessarily. Now we're applying the Kw relationship to strong acids and bases. The key insight is that strong acids and bases dissociate completely, meaning every molecule breaks apart. So if you have 1.0 times 10 to the -4 molar of nitric acid, you automatically get that same concentration of hydronium ions because it's a 1-to-1 ratio. Then you just use Kw to find the hydroxide concentration. Notice how elegant this is. 10 to the -4 times 10 to the -10 equals 10 to the -14. The math confirms everything's balanced perfectly. Now it's your turn to practice. You're working with NaOH, a strong base that completely dissociates. Remember, NaOH gives one hydroxide ion per formula unit, so 3.10 N-2 NaOH means OH- is also 3.10 2 m. Then use Kw to find the hydronium concentration. The second and third questions make you think critically. Calcium hydroxide has limited solubility. It doesn't dissolve completely, so you can't assume all of it ionizes. Barium hydroxide is soluble, but here's the twist. Does that second OH- really come off completely? These nuances separate true understanding from just plugging numbers. Now we're introducing the pH scale itself, the tool that lets us convert hydronium concentration into that familiar 0 to 14 number you've probably heard of. The pH formula is beautifully simple. It's the negative logarithm of the hydronium ion concentration. So if you know H3O-, you can find pH. This is where all those concentration calculations from the previous problems lead us. The negative sign flips the scale. More H3O- means lower pH. We'll use this formula constantly from here on. You're probably wondering what that logarithm actually means. The log is short for logarithm. It's a mathematical function that helps us work with very small numbers like hydronium concentrations. When we write log, we mean base 10 logarithm. Think of it this way. If log x equals y, then 10 to the power of y equals x. For example, log 100 equals 2 because 10 squared equals 100. It's a way to compress those tiny decimal concentrations into manageable whole numbers. That's why the pH scale works so elegantly. Logarithms turn exponential relationships into linear ones. Now here's the crucial question. What are we actually taking the logarithm of? We're taking the log of the hydronium ion concentration, H+. So when we see pH equals log H+, we're plugging in that molar concentration value. For example, if your hydronium concentration is 10 mmol molar, then pH equals log 10 mmol, which equals -3 or 3. The negative sign in front flips the exponent, which is why more acidic solutions with higher H+ get lower pH numbers, and why that inverse relationship works so perfectly. So what exactly is a logarithm? It's the power or exponent to which we raise the base, in this case 10. Think of it as the inverse of exponentiation. If I tell you 10 to the third power equals 1,000, then the logarithm of 1,000 is 3. It answers the question, what power do I need to raise 10 to in order to get this number? That's why when we took log of 10 -, we got -3. The logarithm extracts that exponent for us, which is exactly what we need for the pH formula. Now let's see this principle in action with a concrete example. We have log of 10 cubed equals 3. Here's why. When we take the logarithm of 10 cure, we're asking what power is the base 10 raised to? The answer is 3, because 10 to the third power gives us 1,000. The logarithm simply extracts that exponent, the 3, and gives it back to us. This is exactly what happens in the pH formula when we apply the negative logarithm to the hydrogen ion concentration. The log function pulls out the exponent, which becomes our pH value. Now we're showing you two different ways to write the exact same thing. The top equation uses exponential notation, log 10 cubed, while the bottom equation shows what that actually equals when you evaluate it, log of 1,000. Both give us 3 because 10 core equals 1,000. This demonstrates that whether you see the exponent written explicitly or you see the final result, the logarithm extracts that power. In chemistry problems, you'll often work with hydrogen ion concentrations written in scientific notation, like 10 to the negative 5, and the log function reveals that hidden exponent. Notice that the exponent of 3 in the top equation comes from evaluating the power 10 to core, which equals 1,000. So when you take the logarithm of 1,000, you get that same exponent back. It's 3. The logarithm function literally extracts the power that 10 was raised to. In chemistry, when you're calculating pH from hydrogen ion concentration, you're using this exact relationship. The pH value you calculate is the exponent that 10 was raised to create that concentration. This is why logarithms are so powerful for working with concentrations that span huge ranges. Now let's apply what we just learned to a new problem. We're asking, what is log 1 of 100? Remember, this is asking us to find the exponent. What power do we raise 10 to in order to get 100? Well, 10 squared equals 100, so the logarithm of 100 must equal 2. This is the same principle. We're extracting the exponent. Think of it this way. If 10 raised to some power gives us 100, that power is our answer. This reinforces that logarithms and exponents are inverse operations, working backwards and forwards with each other. Now we're writing this in shorthand notation. When you see log 100 without a base written, it's understood to mean log base 10. We call this the common logarithm. So log 100 is asking the exact same question we just solved. What power must we raise 10 to in order to get 100? The answer is still 2. This compact notation is what you'll see most often in textbooks and real applications. Notice how much cleaner it looks than writing out the full base. Mathematicians use this shortcut all the time because base 10 is so common in science and engineering. Now let's actually solve this problem. We're looking for log 100, which means what power must we raise 10 to in order to get 100? Think about it. 10 to what power equals 100? Well, 10 squared is 10 times 10, which gives us 100. So the answer is 2. Therefore, log 100 equals 2. This is your first logarithm calculation, and it demonstrates how directly these connect to exponents. You're essentially reversing the exponential question. Now, we're rewriting log 100 in a more useful form. Notice that 100 is actually 10 squared. We can express it as a power of 10. This is the key insight. Whenever you see a number in a logarithm, ask yourself if you can rewrite it as a power of the base. By expressing 100 as 10 squared, we're setting up the next step where we can use the power rule of logarithms to extract that exponent and solve the problem cleanly. Now we apply the power rule of logarithms. Since we rewrote 100 as 10 squared, we can bring that exponent down in front. The power rule says log bn equals n log b. Here, log to 10. And remember, log 0 of 10 equals 1, so we get 2 to my 1, which simplifies to our final answer, 2. The logarithm base 10 of 100 is 2, meaning 10 to what power gives us 100? The answer is 2. Now we're shifting from pure mathematics to real-world application. We've mastered how logarithms work using the power rule. Here's the big question. What does this have to do with pH? A neutral solution, think pure water, has a specific pH value that we can determine using logarithms. pH measures how acidic or basic a solution is, and it's defined using a logarithmic scale with base 10. So all those logarithm skills we just practiced, they're about to become incredibly practical as we solve for the actual pH of a neutral solution. Here's the actual pH formula that chemists use. Notice the negative sign in front. That's crucial. The H3O represents the hydronium ion concentration, measured in moles per liter. For pure water at 25 degrees Celsius, that concentration is 110 mg. When we plug this into our logarithm formula, we get pH equals minus log 10, which equals minus 7 equals 7. That's why neutral water has a pH of 7. This formula is your bridge between the logarithm rules we practiced and real chemistry. Now let's actually work through the calculation. We're substituting the hydronium ion concentration for pure water, that 10 mg we found before, directly into our pH formula. Notice we're taking the logarithm of 10 mg. Remember your logarithm rules. Log of 10 to any power just gives you that power. So log of 10 mg equals -7. Then we apply the negative sign in front, giving us -7 equals 7. This is why pure water always has a pH of 7 at 25 degrees Celsius. The calculation directly shows how the math works out. So when we finish that calculation and simplify -7, we get +7. That's our answer. A neutral solution has a pH of 7. This is the benchmark value you need to remember. Anything with a pH below 7 is acidic because it has more hydronium ions. Anything above 7 is basic because it has fewer hydronium ions. The pH scale centers around this neutral point of 7, which is why understanding pure water's pH is so fundamental to the whole acid-base concept. Now let's see how we actually work through the complete calculation step by step. We start with our pH formula and substitute in the hydronium ion concentration for a neutral solution, which is 10 to the -7. When we take the logarithm of 10 to the -7, we get -7. Then we apply that negative sign in front, which turns -7 into +7. This walkthrough shows you the mathematical pathway that gives us that pH value of 7 we talked about before. Now we're shifting our focus to acidic solutions. Remember, an acidic solution has more hydronium ions than neutral water does. That means the hydronium concentration is greater than 10 to the -7. When we plug a larger concentration into our pH formula, the logarithm becomes less negative, and after we apply that negative sign, we get a smaller number overall. So acidic solutions always have pH values less than 7. This is the key connection. Higher hydronium concentration equals lower pH number. Now let's apply what we know about acidic solutions to the pH formula. We use this same equation for all solutions. You just plug in the hydronium concentration. For an acidic solution, that concentration is larger than 10 to the -7. When you substitute that bigger number into the logarithm and apply the negative sign, you always get a result less than 7. So this formula is your tool. Measure or calculate the hydronium concentration, take its log, multiply by -1, and you've got your pH. It's the mathematical relationship that quantifies just how acidic a solution is. Here's a concrete example working through the pH calculation. We have a hydronium concentration of 10 to the -5 molar. That's acidic because it's larger than 10 to the -7. We substitute that into our formula. The log of 10 to the -5 equals -5. Then we apply the negative sign. Negative times -5 gives us +5. So the pH is 5, which confirms this is definitely an acidic solution. Notice how the negative sign in front converts that negative exponent into a positive pH value. Now we're looking at the complete mathematical steps shown together. We substitute the hydronium concentration into our pH formula, then evaluate the logarithm. The key insight is the final line. When we apply that negative sign in front to the negative exponent, we get negative times -5, which gives us +5. This mathematical operation is what transforms the negative power of 10 into a positive pH value, which is exactly what we need for an acidic solution. So we've arrived at our final answer, pH equals 5. This tells us our acidic solution has a hydronium concentration of 10 to the negative 5 molar. Remember, any pH below 7 means the solution is acidic, and a pH of 5 definitely fits that criterion. This numerical result makes intuitive sense. The more hydronium ions present, the lower the pH value becomes, which is exactly what we're seeing here with this moderately strong acid. Now we're shifting gears to explore the opposite scenario, basic solutions. Just like we calculated the pH for that acidic solution, we need to understand what happens when hydroxide ions dominate instead of hydronium ions. Basic solutions have pH values above 7, and we're about to work through how to determine the exact pH when we're given information about a basic compound. This will reinforce the inverse relationship between acidity and basicity on the pH scale. Here's the key insight. We still use the exact same pH formula, even for basic solutions. The formula pH equals negative log of hydronium ion concentration doesn't change. What does change is our starting information. In a basic problem, you'll typically be given the hydroxide ion concentration or the pOH value instead. You'll need to use the water equilibrium constant to convert that information into hydronium ions first, then apply this formula. The beauty of this approach is consistency. One formula works for all aqueous solutions, whether acidic or basic. Now let's work through a concrete example. We're asking, what's the pH when the hydronium ion concentration is 10 to the negative 9 molar? We plug that value directly into our pH formula. The negative log of 10 -storts gives us 9. So this basic solution has a pH of 9, which makes sense. It's above 7, indicating it's basic. This shows that regardless of whether a solution is acidic or basic, we use the same formula and the same process. The key difference was in how we got to that hydronium concentration in the first place. Now we're finishing that calculation. When we take the negative log of 10 to the negative 9, we get negative times negative 9, which equals positive 9. So the pH is 9. Notice the double negative here. That's crucial. The negative sign in front of the log and the negative exponent combine to give us a positive answer. This is why basic solutions have pH values greater than 7, and it's why our answer makes physical sense. Now let's see the complete worked example all together. We started with a hydronium ion concentration of 10 to the negative 9 molar, which is a very low concentration, typical of basic solutions. Plugging this into our pH formula, we substitute and simplify step by step. The negative sign and the negative exponent create that double negative, giving us positive 9. This final answer of pH equals 9 confirms our solution is basic, since it's well above the neutral pH of 7. This is your complete solution pathway from concentration to final pH value. Now let's bring pH out of theory and into your everyday life. This pH scale shows real household products you encounter all the time, positioned exactly where their pH values fall. Notice battery acids sit the extreme acidic end around 0 to 1, while drain cleaner reaches the most basic at 13-14. Your stomach acid around 2 to 3 is quite acidic. That's why antacids exist. Pure water sits right at our neutral 7. Hand soap and household ammonia are basic, which makes sense because they're designed to clean. This visual helps you remember. Products on the left are acidic, products on the right are basic, and everything follows the same pH scale we've been calculating. Now we're diving into the mathematical backbone of pH. The key insight is why scientists use logarithms. Hydrogen ion concentrations vary wildly, from 10⁻n to 10-fold range. A logarithmic scale compresses this into 0 to 14, making it practical. Notice the inverse relationship. As hydrogen ions increase, pH decreases. We also introduce pOH for hydroxide ions and the crucial relationship that pH and pOH always sum to 14. These three formulas are your tools for calculations ahead. Now let's see the formulas in action with real examples. Look at how HCl, a strong acid, produces lots of hydronium ions. Notice how 0.10 mmN HCl gives pH 1.0, very acidic. Compare that to pure water at pH 7, which naturally has 10 mmN H2O-. The salt NaCl doesn't affect pH because it's neutral, but NaOH is a base. It removes H2O from water, driving H2O down to 10, making pH jump to 13. Each tenfold change in ion concentration shifts pH by exactly 1 unit. This table proves the inverse relationship we discussed. Stronger acids have lower pH, stronger bases have higher pH. Now we're diving into the math behind pH, logarithms. A logarithm is just a fancy way of asking, what power do I raise 10 to in order to get this number? When we write log 3 equals 0.477, we're saying that 10 raised to the power 0.477 equals 3. This is crucial because pH uses base 10 logs. The pH formula, pH minus log H2O minus, works exactly this way. So when you see a concentration like 10 numerous quebras, the log of that gives you 3, which becomes the pH. Understanding logs is the key to unlocking why the pH scale works the way it does. We're working through 3 problems about water ionization and pH. First, you'll write the equation showing how water molecules break apart into hydronium and hydroxide ions. Second, you'll use the water ionization constant, Kw, which equals 1.0 times 10 Nietswort at 25 degrees Celsius, to find the missing hydroxide concentration. Finally, you'll apply what you know about strong acids like HCl to determine both ion concentrations. These problems help you understand the relationship between hydronium and hydroxide ions in any aqueous solution. Now we're flipping the process around. Instead of finding pH from hydronium concentration, we're going backwards, calculating hydronium concentration when we know the pH. The key formula to memorize is that hydronium concentration equals 10 raised to the negative pH. In the example, when pH is 1.52, we calculate 10 minus 1 square strength, which gives us 0.30 mem. Notice the important note about significant figures. When working with logarithms, only the digits after the decimal point count as significant figures. So 1.52 has 2 sig figs. Now it's your turn. Use this formula to find the hydronium concentration in fruit juice with a pH of 3.3. Now we're applying this concept to a practice problem. You've got fruit juice with a pH of 3.3, and we need to find the hydronium concentration. We substitute 3.3 into our formula. H3O minus equals 10 mg T. When you calculate this on your calculator, you get 5.0 times 10 to the negative 4 molar. Notice how we express the answer in scientific notation. That's typical for very small numbers like this. Also pay attention to significant figures. The pH has 1 digit after the decimal point, so our answer should have 2 significant figures, which we do with 5.0. This is the pH box, your complete roadmap for converting between concentration and pH. Notice the 4 corners, H mus, OH mers, and POH. The top half deals with hydronium ions and acidity. The bottom half deals with hydroxide ions and basicity. The two-way arrows show you can convert in either direction. The key relationships are H mus equals 10 to the negative pH and OH mens equals 10 to the negative POH. Since pH plus POH always equals 14 at 25 degrees Celsius, knowing one tells you the other. Think of this as your reference sheet for every pH calculation you'll do.